quantum matters, or specifically also with Hirsch, for, let's say, simulating lattice gauge theories and scattering in 2 dimensions, maybe at some point 3 dimensions. And the question was, what type of tensor network, if you want to benchmark these, ultimately maybe you want to do this on a quantum computer, but of course, for now, we also want to benchmark and simulate stuff classically. And the question is, what tensor network is the best practical thing to use? And specifically, we'll talk about the OG of the networks, symmetric product states, and the alternative choice is tree-tensor networks. Yeah, and so we want to learn something about how entanglement costs scale in these, the computation costs for these methods scale in the size of the system we simulate. And to this purpose, we will connect the computation costs to the entanglement scaling in the system. Okay, so first, a short reminder of the network states. Then I will show you some recent activity of where many people start to use tree-tensor networks to simulate 2D systems, also some 3D systems actually. Then we will bound the accuracy of MPS and tree-tensor network approximations of a target state, and also bound the bond dimensions that we need in order to achieve a certain accuracy. Then talk about the entanglement entropies and connect the two, right? And then in the end, we go through some specific scenarios of maybe a system on a cylinder or a torus and determine, at least asymptotically in the limit of large system size, which of these techniques should prevail. Okay, so here the short, and please interrupt at any point, right? Okay, so yeah, the OG of the networks are the matrix product states, which are behind the famous density matrix normalization group method, which was invented by Steve White in the early 90s. Here was formulated a bit differently, not as a variation technique over this matrix product state, but as some type of fancy RG procedure. Then a few years later, Roman Oerston realized that actually, yeah, DMRG is a variational algorithm on matrix product state. And then years after this, a whole zoo of sort of methods was developed. So now we can simulate also not only statics, but dynamics, final temperature, dynamic response functions, open quantum systems, more or less everything you want, as long as the entanglement is sort of 1D area law type. Okay, actually, there's some interesting precursors on Baxter, even before that, I think in the 40s by Kramers and Renyi, you also used some MPS construction actually. Okay, then you can generalize this. So this is mostly suited to 1D systems. So we put one tensor on each lattice site, and then we have, for each site, we have one index of the tensor labeling a local basis state, like spin up or spin down, the sigma here, and then 2 auxiliary indices, which we call bond indices, which are contracted with corresponding indices of the neighboring tensors, which then sort of communicate entanglement in the system. And the degree of freedom are the entries of these tensors. And we can generalize this idea to higher dimensions. So maybe the most direct way are these PEP states, which were pushed forward by Verstraete and Cirac, but also some precursors existed already. Yeah, one main topic today will be these tree-tensor networks. So also here you see the structure of entanglement will not be really 2D-like. So both of these will have the sort of wrong entanglement structure for the type of systems we try to simulate, but for practical reasons, they are still very competitive. So here the difference maybe mostly to MPS is that we have tensors with of order higher than 2 or 3, right, depending on how you count. And then you can generalize these tree-tensor networks, and you get to the Mera states, which is going even deeper into this idea of using a wheel space RG, which sort of, if you look in this direction, you do a wheel space RG. If you see in the opposite direction, you prepare a state by first creating sort of the longest range entanglement and then short range entanglement. And this was proposed by Vidal in 2017. Okay, these are all really great, and we believe that they parameterize at least the corner of the Hilbert space where relevant ground set that we mostly care about, at least in physics, live, right? So we don't want to study arbitrary state, but some specific, let's say, class of ground states or low energy states. And we have reason to believe that the networks, at least these two guys here, and this one, the MPS and 1D, parameterize this corner very well, and we can hence do efficient simulations. One caveat, if you know what to simulate in 2D, is that, okay, these guys, as I said, don't have the right entanglement structure, so it will turn out that these bond dimensions, so the M here is the dimension of the vector space associated to this lag here. Yeah, we call this the bond dimension M. In 1D, like everything is fine, right? We have the computation costs are basically dominated by matrix multiplication, so bond dimension to the power of 3. But if you now put this guy on the 2D lattice, for example, you wrap it like a snake on a 2D lattice, then this doesn't have the right entanglement structure because like physically nearest neighbors would be far in the MPS structure, and this would result in the fact that this bond dimension has to grow exponentially in the system size. Same thing happens for these tree-tensor networks, but in contrast, these PEPs and Mera, they have the right entanglement structure. Big drawback. They have very high computation costs in terms of the bond dimension, right? So instead of like third power here or maybe fourth power here for this Cayley tree, we get 10 to 12 power or even crazier for these Mera states.
I have a question. So, but this is like under some assumptions, right? Like in the worst case, like it shouldn't be contractible. Right?
Yeah, there's already an approximation involved in protecting these. Yeah, that's also a big difference between the PEP states and Mera. Mera you can contract exactly and evaluate observables exactly, energy gradients exactly. In PEPs you already have to do an approximation to get the energy gradient, and hence you can also run into instabilities of the algorithm. So also the optimization algorithm for these two guys are much more stable than definitely for PEPs, and also Mera also has some small issues.
Like there are like known worst cases that are like not going on.
Yeah, non-contractable.
But they somehow generally don't occur. So.
Yeah, you can encode some strange tiling problems into a PEPs and show that okay, in general you can contract the PEPs. Okay, so PEPs and Mera have the appropriate entanglement structure for the systems mostly the systems that we care about. Some drawbacks are that we have these expensive tensor contractions. Also, the optimization algorithms have some challenges. And then in contrast, so as I told you already, MPS and tree-tensor networks are still competitive to simulate 2D3, which is actually kind of embarrassing, kind of meaning that we haven't pushed these algorithms far enough. And the reason is, they have this incompatible entanglement structure, which means that we need exponentially large bond dimensions, but the tensor contractions are very cheap, and we have very good stable algorithm, particularly the DMG method. Invented by Schmidt. Yeah.
So D stand for?
Original gangster. Sorry. I thought this is common in American culture, but yeah. I also learned it just a few years ago. Okay. Okay, so here just some examples that recently there are more and more papers using these tree-tensor networks to simulate 2D systems. This year's data from a very recent paper by the group of Simone Montagnero, where they studied the scattering of magnons in a 2D quantum Ising model, and they went up to 24 by 24 lattice, which is crazy seems crazy if you assume that okay the bond dimensions and hence the computation costs scale exponentially in one of these dimensions here. And what you see is sort of two wave packets which collide, and then you may see some interesting resonances depending on where you are in the phase diagram. Okay.
But what is this shape of the like? Is there like I think of like a Mera-like tree hanging over this lattice, and it kind of goes like.
Yeah, it's this structure.
I should have good attention.
Yeah, I'm counting. 1 point minus. But yeah, another good question with the PEPs, so we had 0 points now. Okay, so there are many applications. Most of them so far were in condensed matter. So Vidal This was one of the early works where they pushed this approach. Moore, Verstraete, and Cirac simulated also 2D systems and developed the method further. Yeah, and then like quantum Hall physics, two-dimensional Ising models, and also like this known dynamics, not only statics. You can study something interesting like roughening transitions, stuff like that. It also been recently applied to nuclear and particle physics models, so specifically quantum electrodynamics. This was both by the group of Montanero. And also tree-tensor-networks are very popular for quantum chemistry problems. And there I think it really makes maybe the most sense, because in a molecule, if it's not a huge molecule, then you have a lot of orbitals and no clear spatial structure, right? So you don't know, like in the, let's say, condensed matter system, we have a clear spatial structure and decay of correlations. So we know sort of which parts of the system are strongly entangled. Often we actually have the so-called area of entanglement. And this is not clear in quantum chemistry problems. And there, sort of, it's more natural to choose this like agnostic tree-tensor-network structure. Yeah.
So PEPS, I know that it can capture the critical behavior of the Ising model in 2D. Can tree-tensor-networks also capture this, or is it always kind of very entangled?
Actually, I mean, PEPs also have the area law. So if you have a critical...
Well, I thought, so you can represent the Ising model as some transfer matrix approach and then encode that in a PEPs.
Yeah.
So you could tune that then to criticality. And there was some annual review of
Yeah, but if you take the 2D quantum Ising model and you are at the critical point, then you expect...
I was talking about the classical, I think.
Classical, yeah, classical is a different story. Yeah, that's
and
it.
then
Yeah.
encoded in the...
Then it works. Yeah, then you have kind of an area law.
Yeah.
Yeah, for tree-tensor-networks, you would have to still increase the bond dimension exponentially in the system size.
I see.
Yeah, so it works, but there will be some crossover at some point.
So I think I remember when people studied saying like a Hubbard model with PEPs, fermionic PEPs, you know, they were just getting these phase diagrams. It was just a complete zoo, like they have no idea, like is it correct, not correct, just like somehow like totally not trustworthy. How about with these tree-tensor-networks? Like, do you have any? Do these papers have any feeling of like, are they like correct? You know?
Yeah. So with tree-tensor-networks, the algorithm is kind of much more controlled because you, if you just cut one bond of your tree, you decompose the system, and we'll talk about it into. You get a bipartition of your system actually, and so in the algorithm you can evaluate efficiently the Schmidt spectrum of your state, and from the Schmidt spectrum you know sort of how close you are to the real state, or you can at least bound how big of errors, or you have some nice scaling, so you can determine these truncation errors, and they usually have a like peaceful, nice scaling behavior, so that you can extrapolate and see how close you are to the exact result.
Is it fully controlled? You actually can, like, as you do a calculation, you can bound and say, I know exactly how much I've neglected.
It depends on whether you really find a nice scaling of the truncation error in your bond dimension. Okay, yeah, so interesting applications in quantum chemistry, for example, Garnet B. Chen also, they improved the methods quite a bit. Schlegeger did some work. This was okay. And then finally, in recent years, also tree-tensor-networks have been used to simulate quantum circuits. For example, Shor's algorithm, some other like small circuits with a group of Christian Mendel in Munich, and also Simone Montanero. They talked about sort of they're just simulating a quantum computer getting digital triggered. All right, so let's try to understand how errors in bond dimensions have to scale in these simulations. So we'll mostly talk about the tree-tensor-networks, but actually matrix product sets are a special case, right? So if you have nice bounds for tree-tensor-networks, you also get bounds for the NPS. All right, so the idea is that we take our system, so we think of, let's say, a system with n sides or n orbitals, and we assign these sides or orbitals to vertices of of a tree graph in some way that is sort of up to you how you. So you can also try to optimize the geometry. Is actually also done of this tree. And now we want to. So we start here from an exact representation of the state, right? So let's say these sigma here are again our local basis states, and this psi is our tensor of the expansion coefficients in this corresponding basis. And now to get a tree-tensor network, we start splitting off one tensor after another. So in the first step, we do some singularity composition of this big tensor here, psi, which sort of where you group these indices 2 to 7 into one super index, do just a matrix SVD, and this gives you one, let's say, unitary matrix or isometric matrix A1, and another isometric matrix which you combine with the singular values to this new tensor psi 1. And then you just continue. Next, we split off with another SVD, this tensor A2, and then we go on, split. Here for now, we do down to any approximations. We just get an exact, and in this way, an exact tree-tensor network representation of the initial state.
So this is like a conceptual thing, like for a big system, you're not going to be starting with.
Yeah, exactly. Okay, so in this way, but we know we can get this exact tree-tensor network structure, and the tensors would obey this orthogonality constraint because they, as you know, from basically unitary from the SVD, right? So if you sum over, so for each of these tensors, let's maybe look at this one. If we multiply A3 with A3 dagger, so summing over this index, and the physical index, you get the identity in this bond here. Which also means that, so this is graphically it's this, and this is the corresponding equation. And this also means that if you cut one bond here, then these tensors actually define an orthogonal basis for this first 3 sites. And this is sort of important once you want to bound the errors. So this is what we're doing here. So as I said, if you're doing the cutting at edge 3, so for this SVD here, these tensors define an orthogonal basis L for sites 1 to 3. The tensor phi 2 here defines an orthogonal basis R for the rest of the system, and we have our Schmidt coefficients. Now we can, if you want to get from our exact tree-tensor network representation to a useful one, or let's say a truncated one, with a finite bond dimension, because usually we want to drastically truncate the bond dimensions, we can achieve this here from this representation by applying these projection operators, where we project onto the MI largest Schmidt coefficients. Right? So we've ordered our Schmidt coefficients here, and P projects onto the subspace with the M largest. And it turns out that applying this projection operator to the state psi, to our target state, is equivalent to inserting this projector P on the corresponding leg of our tensor network. Okay. And for a single projector, it's easy to it's easy to determine the associated loss of accuracy. Right? So we just computed a norm loss, which is given by the so-called truncation error, so the square sum of the truncated singular values. Okay, now, of course, we don't want to truncate on one side, but we want to get some to certain bond dimensions MI on every bond. So we want to insert these small projection operators on the maximum weight component on every edge here of our tree-tensor network. The corresponding state is just a sequence of the corresponding projections. The order here is important because they don't commute. And then you can use sort of a telescope sum to bound the approximation error of this like totally projected state or totally truncated state by the sum of the individual truncation errors.
You said that the order is important, they don't commute, but the bound that you have applies actually to any order.
Yeah, exactly.
Is that ordering any better? Or the one you chose?
This ordering is just important such that we can actually relate the associated truncation error to the Schmidt spectrum of the target state. Right? So if you do first P1, which means that you fiddle around first with this bond here, so you're sort of destroying already your basis or getting an approximate basis for this first site. And then if you do something later on here, then the truncation here would not be sort of the truncation error that you introduce then would not be given by determined by the Schmidt spectrum of the original state, but by the state that's already truncated. Whereas if you go in reverse order, so we start here, so we first sort of reduce the basis for the split system, but we still keep everything sort of here intact. And so this sequence works.
So then you're saying if you did it the other way, that would hold?
Yeah.
No, I think I asked them, so yeah.
Okay, sorry, yeah. Okay, and the way this works is just to write this difference as a telescope sum, and then you repeatedly apply the Pythagorean theorem and also use that the norm of projected state is smaller than the norm of the original state. Yeah, and I should mention that there was like early on, there was this already a corresponding bound derived by Verstraete and Cirac for matrix product states, which is very close to this one. Just this one is one factor 1/2 better, and so their technique didn't kind of work for trees, so had to be a bit adapted. All right. Yeah, so now we want to connect this to entanglement entropy, specifically to the Renyi entanglement entropy. So if you have our Schmidt coefficients for this bipartition here of the system, then the spectrum of the corresponding reduced density matrix of this first part here is given by the squares of the Schmidt coefficients, right? And for the Renyi entropy, you just take the spectrum of the reduced density matrix to the power of alpha. Alpha can be chosen like just as to be larger than 0. Take the log of the sum, and then add this prefactor and this so-called Renyi entanglement entropy. In the limit alpha to 1, you get back the usual von Neumann entropy. But we actually, like for our bounds, we need some alpha smaller than 1 actually to get a bound in the bond dimensions. Anyway, so this is how we can write Renyi entropy for our state. And if you now want to bound the entanglement of the yeah, we can now bound the entanglement in our state by a truncation error for a truncation at a certain bond dimension m. And the way we do this, so we use that the Renyi entropy is a Schur concave function. So this inequality holds here if the distribution rho tilde is majorized by rho I. Majorizes rho I. And so we can just determine the distribution rho tilde, which majorizes all density matrix eigenvalue distributions with the same truncation error as the one that we have in our system. And so, yeah, you get, if you do that, and this was worked out actually as typed by Verstraete and Cirac, so you get this bound here, as long as the alpha parameter for Renyi entropy is below 1. Okay, and we also have a trivial so this would give us an upper bound on the bond dimension that we need in order to achieve a certain energy accuracy if we know something about the entropy in our system. And you also get a simple lower bound on the bond dimensions just by realizing that, okay, the maximum entropy you can encode in the tree-tensor-network is given if you choose the spectrum flat, right, until your bond dimension. This gives you this bound s smaller than log of the bond dimension.
So now you need to check this s, I guess, on every cut. And
Yeah.
then on this cut, if you get satisfied, then you come to that m go smaller.
Yeah. Yeah, you need the entropies for all cuts sort of to work out what the bond dimensions need to be. And actually, you will want to choose if you use networks to simulate a 2D system. We don't want the same bond dimension everywhere. You will have sort of one bond, which is the most expensive one, let's say the one that splits the system into 2 big parts. because there you have this communicates with the most of entanglement. And then if you go lower into our tree-tensor network, so the tensors that encode the short range entanglement, the modulation can be small.
Right.
How tight are these bounds? And should we be concerned about how the tightness varies with output?
Yeah, excellent question. Yeah. So it's not clear how tight they are. You can certainly, if you know the entropy for several alpha, then you can like optimize the bound with a spectral alpha. But in conjunction with the lower bound, you can at least establish that, okay, if let's say both of these guys obey the area law and you're on 2D, so that sort of this prefactor is just this term just becomes a constant prefactor. So we will get area law on both sides here, then we know, okay, that our bond dimensions have to scale according also to some exponential of the area law. So they're not, it's not clear how tight they are. You can certainly work on improving them, which would be interesting. But at least I think you can work out the necessary scaling for the bond dimensions. Okay, so I already mentioned the area law entanglement, so I shortly wanted to just flash this by for those who are not familiar with it. So again, we consider a quantum lattice system with some degrees of freedom assigned to sides of some lattice. We assume that there are these spatial dimensions, and we decompose our system now into a small subsystem A of linear size L, so volume L to the power of D, and the rest of the system, and we ask about the entanglement of these two subsystems. Now it turns out if you pick random states from the Hilbert space, then you will get the maximum entanglement, right? So the maximum entanglement follows the volume law, right? So entropy is extensive in this case, as in thermodynamics, no, statistical mechanics. And the same you get if you pick random states, right? So if you pick random states, you get sort of maximum entangled states, or so at least something that's proportional to the volume law. Also, if you go to highly excited energy eigenstates, you will also find the area law according to this eigenstate thermalization hypothesis. But the story is very different if you go to low energies. So now we look at just the ground states. We will have to distinguish two cases. One, basically, so gap systems. If you have an energy gap, then spatial correlation functions will generally decay exponentially in the distance of these two operators. Whereas if you have a critical system, then you can have then the correlation length can diverge at a critical point, which means that you get to power law decay of correlations.
Those are the mushrooms that we...
Yeah, I should put more mushrooms here. Unfortunately, no mushrooms, so you have to update the slide. Okay, so with this exponential decay of correlation, so finite correlation length, it's quite natural that you would expect this area law, right? So because basically everything that contributes to entanglement between subsystem A and the rest have to be some degrees of freedom that sit close to the boundary of these two subsystems. If you go to a critical case, then it's not so clear because you can think, okay, correlation length diverges, you go from noodles to spaghetti, so everything is sort of correlated with everything, but still there's some spatial decay, and it turns out that you don't go back to the volume law, but you get either an area law or what's called a log area law, so the area law with some log correction. And this depends on whether you have fermions or bosons and whether you're in 1D or higher dimensions. And yeah, so these results are not super rigorous. So there are some rigorous results here for 1D gap systems by Hastings and Van Dau. But for 2D, it's more or less like we have some specific models that you can simulate, or we can do some perturbation, like perturbative field theory, for example, to establish such area laws. For the critical systems, we have just numerics and field theory. You can also derive some rigorous bounds, but just for, in this case, just for non-detecting systems. Okay, but generally you find that this is true for most systems that we care about. There are some very exotic systems, for example, these Motzkin chains. I'm sure maybe some of you have heard of it, Motzkin warp chains, where actually the ground state is similar to a so-called rainbow state, and you get volume law entanglement in the ground state. But they're very somewhat artificial, in the sense that if you, for example, change the boundary conditions, then entanglement suddenly collapses. So it's a bit peculiar. Okay, so now from what we discussed, we finally want to evaluate the cost for our 2D and 3D systems, assuming that we have an area law in terms of the entanglement entropy in the state that you try to approximate with these tensor networks. Okay, so we had this bounds before. So the upper bound was this one we saw, right? With the Renyi entropy. If you assume an area law, then we should find at least in the higher layers of this tree-tensor network, we should really find that the entanglement entropy across this cut is proportional to the area, the surface area, spatial surface area of the corresponding cut. So in this case, this contraction line here, so this edge of the tree-tensor network, this connects the left half of the system to the right half of the system. Right? So the boundary would have a size million L. So you would get here some exponential of L. And there, of course, some prefactors.
So that's bad.
It's bad, right? But it's also bad for MPS. So it's bad for both matrix product state and tree-tensor networks. And I told you before that, yeah, these PEPs and mirror states, which are in principle give you polynomial time algorithms for 2D, they have this very high contraction cost, like 10th power, 16th power, and so on in the bond dimension. So you right now we're kind of at the crossover point, I think, where PEPs and mirror simulations, actually mirror simulations not, but PEP simulations become are competitive with the MPS and tree-tensor simulations, but it's not a clear-cut win for PEPs. It's definitely, like most actually people prefer using MPS or tree-tensor networks to simulate 2D systems at this point.
And to Nicole's question, I mean, that's a bound, but unfortunately, that's probably the true thing, right? Like, it probably could not.
Yeah.
And probably has to be either the edge.
Yeah, because we also have a lower bound. So here, there's a slight caveat here. So we also get an area law for the lower bound. But here, we have to think about the entropy of so this bound was for the entropy in the truncated tree-tensor network, right? And so we also expect that if you have an accurate representation of our state, that this also, if the original state has area law, then okay, the tree also should have an area law, maybe with a different coefficient or something. And actually, yeah, there's some room for improvement here. I think you can connect this back to actually entanglement of the original system with some continuity bounds for Renyi entropies, which are not so great generally. So generally, these continuity bounds. So I'm talking about the Renyi entropy of a state and the Renyi entropy of another state, which has distance epsilon. And you can bound the entanglement of the second guy by the entanglement of the first guy, but the bound involves the dimension of the Hilbert space, which is bad, right? So, but I think if you're talking about area law states, then you can improve this bound. And you should be rigorously show that, okay, this goes back to the same area law, which we also find numerically, right? We just find you produce nicely the area law that we have physically. All right. Okay, so we have that these bond dimensions have to scale exponentially in the surface area of the bipartition of the system, right? So yeah. So as I said, every leg corresponds to connects certain subsystems of our total system, and the area that occurs here is the let's say the size of this interface between the two subsystems. Okay, first example, an MPS on a long cylinder. So you use the periboundary conditions in the y direction. The x direction could be much longer than the y direction, because like if you wrap our MPS in this way around the cylinder, then the boundary of the size of the interface will always be proportional to Ly, no matter like what specific letters you're choosing. So bond dimensions will have to grow exponentially in the y extent of our cylinder, or the circumference of the cylinder, if you want, which means that because MPS algorithms, the good ones have scale in the third power in the bond dimension, so we get this q to the 3 L. For convenience, I've defined this constant q as e to the power of c, right? So c was the prefect in the error law.
Sorry, are you asking us to think of this as we think of this MPS as a tree and use the results from the previous
Yeah,
slide?
yeah, exactly, yeah.
So then I do a cut.
Yeah, so if you let's say cut our system like this, right? Then we're cutting exactly one point. That's one G of the MPS. Right? Yeah, the interface has size L. Okay, now the same scenario, but now with a tree-tensor network. So what we would do is we have first the tree will first split the system a few times in the x direction until we've come to a scenario where the next bond sort of connects square patches of size L times L, right? So the y-extent is now L, and x is a multiple of L. And then once we are at this scenario, once we've come to an L by L patch, then we continue by alternatively splitting in x and y directions to finally get to each individual split. Okay, and we can now break out the sizes of the interfaces for these cuts. So let's say if you just look at this this cut 1 here, again the interface, actually the interface will now be of size 2L, right? Because I said we're splitting many of these patches, so you have this line and another line, let's say some here, right? So interface is size 2L. And then you can work out, for example, for this cut 3. So this would, if you look at this rectangle here, this has size of 3½ times that. Right? So 1/2, another half, another half. Okay, then using here the scaling of the contraction cost. So I won't go into details, but you can also run D mod G on trees, but it has a different cost scaling because now we have tensors like 3-leg tensors, and you get basically the force power of the one dimension, or more precisely, if you have 3 one dimensions here and MA is the largest, then you have to square MA and then multiply by the smaller ones to get the cost, for example, to evaluate observables or energy gradients, and so on. And so from this, you can work out the costs, associated costs coming from each layer. And now there's another like aspect to think about because, okay, a contraction in layer 2 now costs us this q to the 8L, but you could say, okay, I just have very few tensors in layer 2. I have many more tensors, but the number of tensors increases exponentially in the layer index. But it actually doesn't matter. So still the top layers will dominate the cost because the cost decreases double exponentially with increasing layer index, whereas the number of contractions you need to do just increases exponentially in the layer index. So the first few contractions will dominate the overall cost. And so we just have to look at what we have here. So we have q to the 8L, which is much worse than what we have for MPS. Okay, and now we can play this game for different geometries. So yeah, for tree-tensor networks, this is not the nicest geometry. It's kind of the worst you could choose. Let's say we now go to a square. Maybe we want to study scattering or something. Maybe we don't care about this long x direction that MPS handle with ease, but tree-tensor networks have some issue with this long x direction. So let's go back to just having a square system. Then, okay, the costs drop quite a bit from 8L to 5.5L in the exponent, but still much higher than the MPS. And then the best scenario for tree-tensor networks is if you choose a system, a square with open boundary conditions. So then these cuts sort of, because in the initial cuts, this is now not a boundary, right? So it's not an interface between subsystems, so it doesn't contribute to the computation costs. And you go down now to exponent 4.25 compared to 3 in the MPS.
You showed all these papers that use tree-tensor networks. You're saying they used the wrong thing. They should have only used MPS.
That's kind of the question, yeah. I mean, of course, there can be some crossover, right? So it could be that the prefactors are such. There are some polynomial prefactors that I didn't talk about. So coming from the Hamiltonian, for example, Hamiltonian operator, but these are all polynomial prefactors, and yeah, it's not clear what the balance is, and I think you have to test it. But yeah, I would think this argument, at least asymptotically, MPS should win. Yeah.
Could you adapt it to, I know there's IDMRG where you
Yeah.
do DMRG and
Yeah.
you like translate, you assume some infinite cylinder.
Yeah.
I guess tree-tensor networks would be harder to do for that because they aren't naturally like translationally invariant. Has anyone tried to adapt this like TTNS?
Yeah, not really but you can use some of scale invariance. So you can argue that if you have a critical state, then you have like self-similarity in the system, right? Corresponding also to this power law of correlations. So that's a famous property of systems at a critical point, that you get this self-similarity, and that's also what's behind the minimization of schemes. And then you could argue that, okay, these tensors actually have to all be identical.
I see. So
Yeah.
rather than like the translation symmetry that IDMRG takes advantage of, you're doing like some RG basically.
Yeah.
Like you imagine the TTNS as
Yeah.
like doing RG.
Yeah.
I see.
Interesting. I mean, you can argue this, but there are some issues.
Yeah.
Because this structure, this tree-tensor-network structure, this breaks the translation invariance.
Yeah. Yeah.
So choosing, I mean, people have done this, but it's not totally convincing, I would say, because as I said, so the translation invariance is broken by the network structure, and so why should these tensors be allowed to be the same? Maybe like every layer could be the same, but in each layer maybe at least need different tensors. Yeah. Okay. Okay, so we were so this was the best scenario for tree-tensor networks. Maybe the most interesting case, if you want to get rid of finite size effects, then people often use periodic boundary conditions, right? If you can, then in physics you use periodic boundary conditions in order to remove artifacts from the boundaries. And so we would simulate a system like to simulate the system on a torus. For an MPS, that's actually also an issue. So actually, you wouldn't want to do this with an MPS, because then the computational cost increase from third power in the one dimension to fifth power in the one dimension. But you can do a trick and just use an infinite cylinder, right? So as you just mentioned, infinite MPS. So simulating, if you just care about getting rid of boundary effects, then the infinite cylinder is actually better than the torus. So you would use this and go back to this third like factor 3 in the exponent. For the tree-tensor networks, you go back to the reverse scaling, right? So you go back to the long cylinder, so 8 in the exponent. Okay, then you can repeat this analysis. So I sat down like for a day and did this for 3D. Different scenarios here. You again find that the MPS win. So you have, let's say, if you're the physically most interesting case are having periodic boundary conditions in all directions, then you would have again this difference of factor 8 and factor 3, and the difference to 2D is now just that we've gone from L in exponent to L squared in exponent, because now the interfaces are of course planes instead of lines. Okay, so this looks pretty bleak for tree-tensor networks. If you have open boundary conditions, then I think it's conceivable that there could be some competition if the polynomial prefactors are really large for the MPS.
So can you like not even come up with a geometry where the trees work? Like, would it work in a tree?
Yeah, in a tree it works, yeah. Yeah, in a tree, yeah, for a tree, if you have an area along the tree, then the bond dimension is independent of the system size. Yeah. And people actually have studied quite a lot of papers, because it works, people have studied it.
So you put a paper up earlier. If you can ignore this question, if ignore it, but there was a fractional quantum Hall paper. Were they looking at an open boundary condition where it's like competitive?
I'm not sure. I have
Okay,
to. Yeah. Very good question. So the general argument of why people think that tree-tensor networks might be better is that the distance of physical sites, so the graph, in terms of the graph distance, is much lower than what you have in an MPS, right? So if look at any two physical sites here, then the distance in the tree-tensor networks is at most log L, because we just have log L layers, right? In our tree. In contrast with the MPS, if you wrap our MPS over the cylinder, then the typical graph distance is L to the power of d minus 1 if d is the number of spatial dimensions. So much worse. So that's why people generally think that tree-tensor networks should be beneficial. But at least according to this analysis here, I hope there's no mistake. What outweighs this benefit is the more costly truncation of the tree-tensor networks. And we've just taken, actually for this purpose, we've just taken the binary trees. You could also think about like trees with vertex to be 4 or higher. Yeah, even for the binary tree, which is the cheapest in terms of contraction costs, it seems that MPS wins.
But you also said that we can think of MPS as a tree, right? So like then there's a whole family of trees, I guess, that interpolate from the MPS, which is also a tree, to this thing, which is also a tree.
Yeah.
And is MPS the best tree out of all trees?
When you have to do it in a way that you can scale up the system, right? So I'm not sure what the construction would be, but probably I would assume the answer is yes. Yeah, I forgot to like add an advertisement here. So I actually recently wrote a paper with a student where we use constraints on these tensors in this and the tree networks are also PEPs and so on. So we constrain the so-called CP rank of the tensors. So we write each tensor as a sum of tensor products. Yeah, so so you just write
Many.
okay. Yeah, so if you have a tensor with let's say 3 indices, well, let's say sigma 1, then some indices A, B, C, which are contracted with corresponding indices of neighboring tensors, and we would write this as 1 to K, and let's say vector alpha A times beta B gamma C, I guess. Not doing a very good job here. Plus some delta times delta sigma, something like this. And you constrain so basically you write the tensor as a product over vectors, right? Alpha, tensor beta, tensor gamma, tensor delta, and you constrain the number of terms. This is so-called CP rank. And in this way, in this way, we can drastically reduce the contraction costs. So that's another thing that we can play around. So go away from these tree-tensor networks with unconstrained tensors to number of constrained tensors. The game can completely change. Right? All right, so what's my new camera right now? I want to conclude. So we talked about short-wave network states, which are a nice variation approach to study quantum many-body systems. Showed you a lot of flashed by a lot of examples of people using tree-tensor networks to study 2D system or even 3D systems. We connected the MPS accuracy and bond dimensions to the Schmidt spectrum and also the Renyi entropies. And then based on the fact that in most systems we care about, we have an area law or log area law, we were able to determine the scaling of computation cost of MPS and tree-tensor network for 2D and 3D systems, which obey this area law. And the bottom line was that it seems that MPS win, at least if we go to large system sizes. Of course, these problem prefactors could mean that for small systems, okay, the trees could still win. All right, and there was another thing like that. Okay, yeah. And I would like to thank you for attention.
So is this tree-tensor-network sort of the best competitor? Like you showed all these other things, you know, MER and PEPs, but those are even worse, right? PEPs, I mean, it's not controlled, right? So like basically MPS is just better, but it's just better than anything that we know.
No, I mean, asymptotically, PEPs should win.
But it's like,
Perhaps it's controlled.
Well, yeah.